Very first of all, we are proceeding with the matrix. Now, whatever we have done yet now what is the form of matrix, how the matrix is formed, or where are we, the matrix we are getting, then the operation of the matrices with the different types of matrices, what is the order, what is an element, like that. So last one topic was the matrix addition, and there we have found we can write any matrix with like that, suppose Aij with the element notation, and if the order of the matrix is m cross n, then another matrix that is of Bij with the same order, then we can do the matrix addition. That means for the matrix addition, the two matrices have to be in the same order. Now, not only for two matrices, if we have any number of matrices with the same order, suppose another one, Cij m cross n, that means the same order, the result is like that, the same Aij plus Bij plus Cij with the resultant matrix of the same order. That means whatever the matrix orders are, we are getting the resultant matrix with the same order. Next one, what are the properties? Properties of matrix addition. And the very first one is called the commutative property or commutative law. What is a commutative property? Suppose we have any type of normal number system. Suppose 1 plus 2. In any normal number system, that one is called, the sign is called the addition. Now, when we have 1 plus 2, we are getting the same result if we write 2 plus 1. That means whatever the number is on the left hand side of the plus operation and whatever is in the right hand side of the plus operation, if we interchange the both, that means now the left one is the right one is the left one, the result is the same, then we may say the addition follow the commutative law. That means A plus B is equal to B plus A, not the number, practically the operations. Operations is here, the plus. The operation is following the commutative law. Same as, suppose we have 2 is a number, then the multiplication sign, and then 3. Then we are getting 3 cross 2. That means for the multiplication operation with the real numbers, the 2 is on the left hand side of the operation, 3 is on the right hand side. Now we are interchanging, that means A cross B, that is also B cross A. So we may say the multiplication or the product operation is also following the commutative law. Let us suppose another number, two numbers, 3 minus 2. So that is the subtraction, but that is not equal to 2 minus 3. So that means the subtraction operations is not following the commutative. So the operation is the important thing. That is the sign, that is the operation which is following that type of. As like the subtraction, the division operation is also not following the commutative. Now those are for the real numbers. Now when that is, we are proceeding with the matrix addition. What is happening? Suppose we have a matrix that is A with the order n cross n, then we are adding that plus operation, and that plus operation is different. That plus operation is practically for the real numbers. That plus operation is called the matrix addition operation. Both are different because A is not a number, A is a matrix. Another one, suppose B, n cross n. If we proceed with that, whatever be the result is, that is also true that B m cross n plus A m cross n, that is same. Okay, let's check one. Suppose we have a matrix A that is of order, suppose 1, 2, 3, 4, 5, 6. That means 3 row, 2 columns. And we are adding with B, that one, suppose once again have to be the same order, that means 3 cross 2. So suppose 10, 20, 30, 40, 50, 60. Now at first we are adding. So after addition, like that, 1 plus 10, 2 plus 20, 3 plus 30, 4 plus 40, 5 plus 50, 6 plus 60. Now we know the normal addition follow the commutative. So we may write that one as 1 plus 10 as 10 plus 1, 20 plus 2, 30 plus 3, 40 plus 4, 50 plus 5, 60 plus 6. Now after that we are decomposing. Decomposition means just whatever we have added at that moment with the matrix addition, we are now just decomposing it, just dividing it. So the first 10, 30, 50 would be here in the first column, 10, 30, 50, 20, 40, 60, plus 1, 2, 3, 4, 5, 6. So at first we had A plus B. Now that one is equal to B plus A. So we may say the matrix addition A plus B is equal to B plus A, follow the commutative law. Okay, is that right? Okay.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay, next one, we are proceeding with another one that is called the associative law. That is also same with the law that is following with the real number system. Suppose we have 1 plus 2 plus 3, where we have using the parentheses with the 1 and 2 operations. That means at first we are proceeding with the addition 1 and 2, then we are adding 3. That is also same, giving the same result if we add 2 and 3 at first, then add 1. That type of operation, that means plus at that moment, giving us the result, it is following the associativity. That means A plus B plus C is also B plus C plus A. Same as if we proceed with any type of multiplication with real number, 2 cross 3 with 6 is equal to 3 cross 6 at first, then with 2. So that means the multiplication or the product operation also follow the associativity. Let's check with the subtraction. 2 minus 3 minus 6 is not always 2 minus 3 minus 6. Okay, or the division, not always. Okay, so that type of operation is not always following with the associativity. But what is happening with the matrix associativity law? Let's check. Suppose we have a matrix A, that is we are proceeding with 2 cross 2, suppose 1, 2, 3, 4. Okay, Shomodeep, any question?
No, sir, question nahi.
Okay. 1, 2, 3, 4. That is 2 cross 2. B, that one is suppose 5, 6, 7, 8. That is also 2 cross 2. And C, that one is equal to 9, 10, 11, 12. that is also 2 cross 2. Okay, so A, B, C. So we are at first proceeding with 1, 2, 3, 4 plus 5, 6, 7, 8 plus then 9, 10, 11, 12. Writing the way of associativity. At first, we are proceeding with A plus B, then we are proceeding with C. Let's check. At first, we are adding A plus B, that is becoming 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8. Then 9, 10, 11, 12. So here we are giving A plus B, that one C. Once again, we are adding. So that is 1 plus 5 plus 9, 2 plus 6 plus 10, 3 plus 7 plus 11, 4 plus 8 plus 12. But here we are adding some more. That means as we are adding 1 plus 5 with 9, so we are using the parenthesis here. 2 plus 6, 3 plus 7, 4 plus 8. Now the near number system follow the associativity with the plus or addition operation. So 1 plus 5 plus 9 can be written as 1 plus 5 plus 9, 2 plus 6 plus 10, 3 plus 7 plus 11, 4 plus 8 plus 12. Now, once again, we are decomposing. So, decomposition occurs and we are getting like that 1, 2, 3, 4 plus 5 plus 9, 6 plus 10, 7 plus 11, 8 plus 12. So that means it is our A, it is our B plus C. So we can once again can write 1, 2, 3, 4 plus 5, 6, 7, 8 plus 9, 10, 11, 12. So that means we may write it as A plus B plus C. So that one is following our A plus B plus C. So matrix addition follow associativity law. Now the associativity law. Next one. Remember the term that is called with the matrix addition, that is existence of additive identity. Identity means whatever you have, what is that particular value you are giving or finding the same value. And that additive means identity may be of different type with different operation. At that moment, we are considering with the matrix addition. So that's why that additive means we are concerning with the matrix addition sign or matrix addition operation. Whatever the identity we are getting, and that is connected with the null matrix. That means a big O, 0. Existence means it exists. Let we have a matrix that is A, and obviously that one must be non-zero or non-null matrix. Suppose any matrix we are writing here, suppose 3 cross 2 of order. Then suppose we have A is equal to 1, 2, 3, 4, 5, 6. For non-null, it has to be of the same order if as we are proceeding with the addition sign or the plus sign. So the order of null matrix is like that 0 0 0 0 0 0 or 3 cross 2. So if we write A plus O, that we are getting A. That is also same if we add with the null matrix on the left hand side with the matrix addition and right hand side the non-null. The difference is that one, that is the matrix addition operation, that is the matrix addition operation. At first on the left hand side the non-null, right hand on the null, and here left hand is the non-null, right hand is the non-null. Let us check with an example. Suppose A is equal to 1 2 3 4 5 6. So here we are giving 1 2 3 4 5 6 plus 0 0 0 0 0 0. So we are getting 1 2 3 4 5 6, and that is also same as 0 0 0 0 0 0 plus 1 2 3 4 5 6. So that means we may say A plus O is equal to A is equal to O plus A. As the matrix exists, that's why existence, as it is for the matrix operation addition, that's why the additive, and as it is giving the same, that's why it is identity. So that means any non-null matrix when added with the null matrix, obviously of the same order, otherwise the matrix addition is not possible, then the matrix exists itself. That is called the property of existence of additive identity. Is that clear?
Yes, sir.
Yes, sir.
Okay.
Yes,
Next term.
Yes, sir.
Okay. Next term is once again another one. Existence of additive inverse. Before we proceed to the additive inverse, it's better another property of matrix we proceed. Just keep it blank, and here we are proceeding with another property that is called the scalar multiplication with a matrix and obviously non-null. Okay, scalar means any number at that moment. Suppose we are writing it as A or K most of the time. That is a general term. Non-null means A, it may be of any order. Suppose we have the number is equal to 5 and we have the matrix like suppose 3 cross 2, 1 2 3 4 5 6. Okay, so when we are multiplying it with 5, that means here we are writing K into A as 5 into 1 2 3 4 5 6. Remember, in the case of matrix, each and every element of the matrix must be multiplied with the scalar. Just important thing is each and every element. So what is going on here? Just check. 5 cross 1, 5 cross 2, 5 cross 3, 5 cross 4, 5 cross 5, 5 cross 6. Obviously, the order must be the same. So as usual, 5, 10, 15, 20, 25, 30. That is called the matrix multiplication with a scalar. What happens if we have a matrix A and on the right hand we are multiplying it? That means 1, 2, 3, 4, 5, 6. And here we are multiplying the k as -1. The result is same. We are multiplying the -1 with each and every one. So that means -1, -2, -3, -4. Suppose here that one was -5. So that is becoming 5. That one is -6. So that is called also the negative matrix, because whatever the matrix elements was, we are practically writing like that. Just a moment. Is it viewable now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
sir.
sir.
Yes, sir.
Okay, okay, okay.
Yes, sir.
Yes, sir.
So that is called the negative matrix. Okay. So here, whatever be the signs of the elements where that has been on the opposite sign. If that one was plus, that is now minus. So it is written in that way 1, 2, 3, 4, 5, 6, or we may write it as if A is that one. So when we are multiplying it with -1, we are getting -A, and that one is called the negative matrix. That is the normal case of matrix multiplication with a scalar. Now, that one, existence of additive inverse. Already we have known what is the meaning of inverse matrix. So inverse, that term, additive, that one is based on the matrix addition, and once more that is based on the result that it exists. So that's why existence. So whatever be the property is A plus, that means operation matrix addition with A, the inverse matrix of that particular matrix, we are getting the result, that one is null matrix. Or if the inverse matrix is at left hand side of the matrix addition operation and on the right hand the A, that is we are getting same result. Suppose we have 1, 2, 3, 4. So obviously its inverse would be -1, -2, -3, -4 is equal to, we are getting, that is 0, 0, 0, 0, 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4. At that moment, I am subtracting directly, but just we will proceed with the subtraction. Then, if that one are both same, okay, so that is called the existence of additive inverse. As it is existing, that means the inverse is existing, and that is based on the addition, and we are getting the null matrix or the zero matrix. Next property or next operation, sorry, that means which one is called the subtraction of matrices. If we say the addition, okay, very much, that's very good, that m cross n must be added with m cross n. That is possible. Second one, if we consider the matrix multiplication with scalar, that is possible. Same thing, m cross n when multiplied with any k or any scalar, we are getting the resultant matrix as of same order. So that is also possible, but mathematically or theoretically, subtraction of matrices are not possible. Why? Suppose we have a matrix that is A, and suppose that one is 1, 2, 3, 4, and B that is 2, 3, 4, 5, and you are proceeding with that A minus B, and you are saying, sir, that is very much true that it is 1 minus 2, 2 minus 3, 3 minus 4, 4 minus 5. So whatever we are getting minus 1 minus 1 minus 1 minus 1, that is very much true. The answer is also perfect. But whatever you have done here, A minus B, that is practically not a single operation. That is the combination of addition and matrix multiplication with the scalar. That means just check here, A minus B, that means A plus minus B. Moreover, that one is A plus minus 1 into B. So that means that is the addition that is called matrix addition, and that one is scalar, which one is minus 1 multiplication with non-null. But numerically, if we proceed with the result would be same. So that means we can write that is whatever we have written here, 1 2 3 4 or 2 3 4 5. So I am writing it 1 2 3 4 plus minus 1 into 2 3 4 5. That means that one is A, that one is B, that one is minus 1, that one is plus. So the result is like that, 1 2 3 4 plus minus 1 multiplies, so minus 2 minus 3 minus 4 minus 5. So that means the operation is going on 1 plus minus 2, 2 plus minus 3, 3 plus minus 4, 4 plus minus 5. So obviously that one, 1 minus 2, 2 minus 3, 3 minus 4, 4 minus 5. So minus 1, minus 1, minus 1, minus 1. So result is same. So when you may ask that when the subtraction we are proceeding with matrix, we have to show that type of steps. No, there would be no problem if we do that direct step. But remember, each and every time, matrix subtraction is not a single operation. It is practically the operation of a combination of the matrix addition with the matrix multiplication with scalar. Next one operation is called the matrix multiplication or the product of matrices. That is means the multiplication of matrices. Now very much important. Why? Now when we have addition, we can proceed with the same order. That is true, and we are getting the result as m cross n. When the matrix multiplication with scalar, there is no problem. Whatever be the matrix is order, we are getting the same result. That means same order. Now the matrix addition. Suppose we have a matrix A, another matrix B. For the matrix multiplication, suppose the first one, that means whichever is on the left hand side of the matrix multiplication operation and on the right hand are very much important. Suppose that is m cross n and that one is m cross p. Both are different order. For matrix multiplication, it has to be completed or possible if the left hand matrix column number has to be equal the right hand matrix row number. That means, suppose if we have A 3 cross 2 cross B 2 cross 4, here we have that one column number 2 is equal to its row number 2. So matrix multiplication is possible. So the left hand order and right hand matrix order both are very important. And what should be the resultant matrix? A cross B. That must be with the order, very first one, which one is our left hand, that should be on the first. Then its column is the right hands. That means M cross P. But before that, the column number of the left hand matrix has to be equal with the row number of the right hand matrix. So here what should be the resultant matrix? That is A, B, 3 cross 4. Okay. Next one, suppose same matrices A and B. So we are writing on the left hand 2 cross 4 cross A 3 cross 2. Here we may check that one is the 4, that one is the 3, not equal to. So matrix multiplication is not possible in that case. So the same matrices A cross B is possible, but B cross A is not possible. Sometime. Okay, it may possible, it may not be possible according to the order. Let's check with some example. At first, suppose we have a matrix that is A with order, suppose 3 cross 2. Okay, so 3 cross 2, 1, 2, 3, 4, 5, 6. 3 cross 2. Another one matrix, suppose B, that is 2 cross 4. That means 3, 4, 5, 6, 7, 8, 9, 10. That is 2 cross 4. So both have different order. What should be the resultant matrix? We know that must be 3 cross 4. So if we write the element A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34. That means, just look, 3 rows, 1, 2, 3, 4 columns, 1, 2, 3, 4. Now look at the element number. First one is first row, first column, first row, second column, first row, third column. Okay, like that. So here are also we proceeding with the same. Just look. What should be the first element? First row, first column. That means first row, first column. So multiply like that. 1 into 3 plus 2 into 7. Once again, each and every element of the first row or the row must be multiplied with the each and every element individually with the elements of the first column, and also the plus sign must be there. That is our A11. So the next element is A12, first row, second column. So that must be first row, second column, like that. 1 into 4 plus 2 into 8. Third one must be our A13, fourth one must be A14. So we may proceed with that. Okay, so first row, third column, first row, third column. So like that, we are writing here 1 into 5 plus 2 into 9. First row, fourth column for the next element. That means first row, fourth column. So that one must be 1 into 6 plus 2 into 10. In the same way, 3 cross 3 plus 4 cross 7. 3 cross 4 plus 4 cross 8. 3 cross 5 plus 4 cross 9. 3 cross 6 plus 4 cross 10. If we draw the same thing once again, just like that. 3, 4, 3, 7. Second row, first column, because the element is second row, first column. Second row, second column. Second row, second column. Third one, second row, third column. Second row, third column. Next one, second row, fourth column. 3, 4, 6, 10. So the next one would be third row, first column. That means 5 cross 3 plus 6 cross 7. Then 5 cross 4 plus 6 cross 8. 5 cross 5 plus 6 cross 9. And last one, 5 cross 6 plus 6 cross 10. So obviously the result of the order is 3 cross 4. Now whatever be the result after calculation, whatever we are getting, I am not calculating it, but the main thing is there. So that means if we consider like that, the first one must be 3 plus 14, that means the 17. Like that. The second one, 16 plus 4, that means 20. 18 plus 5, that means 23. Like that. Is that clear now, the matrix multiplication here about?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, next
Yes,
one.
sir.
Next one, the same thing. Same thing, we are going now with the B cross A. The same matrices. Now, what is going on here? Just example 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, 5, 6, 7, 8, 9, 10. That is 2 cross 4. Another one was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That one is originally 3 cross 2. We know that is not possible because that is 4 is not equal to that is 3. Wrong. But what is happening? Let's check. First row, first column. Suppose I am trying to multiply 3 with 1, no problem. 4 with 3, no problem. 5 with 5, no problem. Then where is 6? With which we can multiply the 6? There is no possibility. Same as 7 with 2, 8 with 4, 9 with 6, but what to multiply with 10? There is no possibility. So that's why at that moment, A cross B is possible, but B cross A is not possible. That is not possible. So that is also giving us another one property. Which one? Already we know for the commutative property. For the commutative property, we have A plus B is equal to B plus A for matrix addition. But in that case, or in the case of product, we can see A cross B, not always B cross A. Even sometimes B cross A is also not possible. So matrix multiplication does not follow the commutative law. Okay. Next one, whatever the first question was, that is, said something about idempotent law. Already we have that one. Idempotent matrix. And in the case of idempotent matrix, whatever we have found, now when we have a not null matrix, that is A, and if we have A square is equal to A, then we must say that A as the idempotent matrix. So here, suppose we have an example like A is equal to 2 minus 3 minus 5 minus 1 4 5. That is according to your Paldash book also. 1 minus 3 minus 4, and last class already that was the idempotent law, idempotent example. So we have to find out the A square. So A square means A into the same matrix 2 minus 3 minus 5 minus 1 4 5 1 minus 3 minus 4. That one was 3 cross 3. That one is also 3 cross 3. That 3, that 3. Its column number, its row number, both are equal. So that is true. With the multiplication is possible. So we are multiplying. And we are multiplying the first row, first column at first. So 2 cross 2 plus minus 3 into minus 1 plus minus 5 into 1. Second one, 2 into minus 3, first row, second column, plus minus 3 into 4 plus minus 5 into minus 3. Third one, first row, third column. So that means 2 into minus 5 plus minus 3 into plus 5 plus minus 5 into minus 4. Now the next one, minus 1 into 2 for second row, first column, plus 4 into minus 1 plus 5 into 1, minus 1 into minus 3, 4 into 4 plus 5 into minus 3. Second row, third column, minus 1 into minus 5 plus 4 into 5 plus 5 into -4. Third row, first column, 1 into 2 plus -3 into -1 plus -4 into 1. 1 into -3 plus -3 into 4 plus -4 into -3, and 1 into -5 plus -3 into 5 plus -4 into -4. Let's check what are the results at first. So that is 2 into 2, 4 plus -3 into -1, that means 3, 4 plus 3 minus 5, 7 minus 5, that is 2, -6 minus 12 plus 15. So whatever is plus 15 minus 18, that is -3. Now -10 minus 15 plus 20. Result is -5. -2 -4 5. So -1. 3 plus 16 minus 15. That means 4. That one 5 plus 20 minus 20. So the result is +5. 2 plus 3 minus 4. 5 minus 4, that is 1. -3 minus 12 plus 12. So that one is -3. And finally, -5 minus 15 plus 16. So the result is -4. That one is our A. So we can say A square is equal to A, or A is the idempotent matrix.